Hello and welcome back to my channel. In this video, we'll be talking about acceleration due to gravity. Well, gravity is something that we all experience and something that we all deal with on a daily basis. If you jump up right now, the force that's going to bring you down is called gravity, right? That's the thing that that's the thing that keeps everything on the ground. Maybe you'll see online videos of people in the International Space Station and they're able to float around. Well, that's because there's no gravity there. There's nothing keeping them down. But gravity also has an acceleration. It's like a force that's constantly pushing us down. And every time we stand up and walk, we're opposing gravity, right? And that's like oftentimes how maybe you'll see older people have some skin hanging down a little bit, or some of their skin is like sagging a little bit. Well, the reason that happens is because gravity has been tugging at their skin for like decades and decades to the point where the skin actually starts to droop down a little bit. So if you're ever wondering why older people sometimes have their skin hanging a little bit, it's because gravity is constantly pushing down on us every time. But in this case, when we're talking about acceleration due to gravity, well, then acceleration due to gravity can be seen as whenever we let an object free fall. So whenever an object is free falling. Whenever an object's free falling, you can say that is the acceleration due to gravity. But what is the meaning of like a free fall, and what is that? Well, free falling basically means or implies that there is no air resistance. And in everything that we cover in this course in particular, there will be no air resistance with what we're dealing with, because everything that happens in a vacuum. No air resistance is actually only in a vacuum, but everything that we deal with, we're going to assume no air resistance, because that would make it overly complicated, which is something that you will work with later in the future, but not at this point in physics. But what is the symbol for gravity? Well, the symbol for gravity is simply just a lowercase g. So whenever you see a lowercase g, you can assume that to be gravity. What is gravity equal to? Well, gravity, because it's a constant, right? Gravity isn't like just a variable from before, how acceleration, we had acceleration, and then acceleration could be different things. Gravity is actually a constant that's existing all throughout Earth. The gravity we experience in Ontario is going to be the same gravity that we experience in another part of the world. That's why gravity is something that we'll always have. Whenever you're looking at a question and you're wondering, oh, like, what's something that I also need for this question? Well, you'll always have gravity when you're solving these questions, because anytime we're on the surface of the Earth, we have gravity as a constant value. And gravity as a constant value is equal to, so G is equal to 9.80 meters per second squared. It's acceleration because as you fall down, let's say you jumped off a building, you would start to gradually accelerate as you're getting closer and closer to the Earth. So that is basically what gravity is and how we accelerate on the surface of the Earth. Next, we'll look at some practice problems, and how we can apply gravity to some of our physics problems. Okay, so we have a question here, and it says a flower pot is knocked off a window ledge and accelerates uniformly to the ground. If the window ledge is 10 meters above the ground and there is no air resistance, how long does it take for the flower pot to reach the ground? So let's begin by getting our given down. So we know that the flower pot is 10 meters above the ground. So we can go our delta D is equal to 10.0 meters. And we know that because if this is the ledge right here, if this is where the flower pot fell off of, like this, the direction it's going in is down. So we can set down is equal to positive. So now that we set down as positive, we can come here and we can get the next piece of work given down. So we have the direction, and we know that it's accelerating uniformly. How long does it take for the flower pot to reach the ground? We know that we have our gravity, which is always constant, which is also a vector, because gravity is going downwards, so make sure to include a vector sign on your gravity. But 9.80 meters per second squared. Up here, you should also add a vector, realistically, because gravity is a vector. It has a direction, which is always downwards. So you should always add a vector on your gravity as good measure. But let's continue. As far as reach the ground. So what we're really looking for is, now we can go into our required to find. We're looking for how long does it take for the flower pot to reach the ground. Because it doesn't give us an initial velocity, it just says the flower pot is knocked off. We can assume that before the flower pot was knocked off that it was sitting still. So we can just assume V1 is equal to 0. So now we can try to think what we can do. Well, we can reference back to our previous video and try to use some of the equations and motions and try to apply them here. And in this case, our gravity is actually also equal to our acceleration towards the ground, because we're accelerating toward the ground. So in this case, when we use delta D is equal to 1/2 A delta T squared plus V1 delta T, instead of our A, well, our A is the same as our G because we're accelerating downwards. Just like if I were to drop a pencil on the ground, it's accelerating downwards. Our A is our G, it's accelerating downwards, but at 9.80 meters per second. This is the rate at which gravity is moving down at. So now we're just looking for T. Well, to find T, we have to rearrange this equation. So let's see what we can do here. We can go delta D is equal to 1/2 A delta T squared. But because V1 is 0, we can just drop this whole term out. So now we're just left with delta D is equal to 1/2 A delta T squared. So we want to try to get rid of some of these terms here. So first, the first thing we can do is we can multiply by 2 because we have a 1/2 here. But if we do the opposite of a half, which is multiply by 2, we'll get rid of the 2. And we're multiplying by acceleration. So we want to do the opposite of multiplication, which is division. So divide by acceleration here. And now we'll end up with 2 times delta D vector over A vector is equal to delta T squared. Now we also have this square sign here. So we don't want that there because that's going to mess up our equation. So what's the opposite of squaring something? Taking the square root of something. So we can take the square root of the whole term, and that'll cancel out the square. So we're left with 2 delta D vector over acceleration. Take the square root. Now you have delta T all by itself. Now from here, we can just plug in the numbers and get the solution. So we can take the root of 2 times 10.0 meters over 9.80 meters per second squared and equal that to delta T. And now that we have this is pretty much all just calculator work. So we can determine what that is. Let me punch that into my calculator. So you get 2 times 10, divide that by 9.8, you're left with 1.4 seconds is equal to delta T. And according to significant digits, that's technically, because there's 3 significant digits in both of these, we should have 3 in our final equation. So we should have 1.43 seconds is equal to delta T. And that is our final answer. Let's go on to the next question. The next part of this question is a part B. And this part is asking, what is the final velocity of the flower pot just before it hits the ground? So we can use our same given from up here. So we can again set down as positive. And we can just go delta D is equal to 10.0 meters. G is equal to 9.80 meters per second squared, which is also equal to our acceleration in this case. And V1 is again 0. Are required to find this time is not T, but is rather V2. Now, there's a few equations we could use from our previous examples. And you may argue that we should use some of those equations because now that we have time, we can use equations with time and V2. But what if this time that we calculated up here was wrong? Now if you use the wrong time down here, you have more margin for error to have your next answer wrong as well. So to avoid this, we should use an equation that doesn't involve the value that we calculated for, but only the numbers that we have. So we have less likelihood of making an error. So what equation that could we use that could help us get V2? Well, one equation that we could use is V2 squared is equal to V1 squared plus 2a delta d. This equation works out very well. We can just drop out our V1 term here to 0 because it's 0. We're left with V2 squared is equal to 2a delta d, put vectors. And now we have V2. Actually, we still have to take the square root because we have a square root sign right here. So now V2 is equal to 2a delta d, the root of all of that. And now we can just jump to our solution. So V2 is equal to root 2 times 9.80 meters per second squared times 10.0 meters. And that gives you 2 times 9.8 times 10 will just give you, when you take the root of that, it gives you 14 meters per second. So right before it hit the ground, because when what our V2 really is when the flower pot is right the second before it hits the ground right here, the velocity on this flower pot was 14 meters per second. So I hope you learned something from this video, and in our next video we will be moving on out of this chapter and we will be going into motion in 2 dimensions.